Hey limnologists, let's dive into chemical limnology and water chemistry. This introduction is going to focus on the following topics: why water chemistry is important, some of the water chemistry basics, what we find in water, how we measure water chemistry, the major sources of ions in fresh waters, and we're going to finish up by talking about pH. So why is water chemistry important? Well, one thing we've already discussed is the influence of water chemistry on physics. We've already learned that the presence of salt influences the density of fresh water. And so if there's a lot of dissolved salts in a lake, there's potential for the lake to be meromictic. And if lakes don't mix, that has huge implications for biology. In fact, oceanographers are so obsessed with salinity because it, along with temperature, drive ocean circulation, which influences our planet's climate. And unlike the oceans, which actually have a pretty narrow range of salinity, you could find inland waters that range from almost pure water to water 10 times the salinity of the ocean. And that wide range of water chemistry that we see in inland waters influences biology, because most species are only adapted to live in a very narrow range of water chemistries. In a later video, we'll take a look at some of the extreme lakes found on Earth and their bizarre water chemistry, but for the remainder of this video, we'll focus mainly on freshwater environments. Understanding water chemistry will help you understand what species might be living in that environment, and this becomes front and center when thinking about invasive species and suitable habitats. Take for instance zebra mussels. An invasive species in North America, zebra mussels have colonized many lakes, impacting both infrastructure and food webs. As it turns out, zebra mussels need calcium to build their shells, so don't tend to grow in lakes that have calcium concentrations less than about 17 milligrams per liter. So if you're a natural resource manager charged with preventing the spread of zebra mussels, you could look at water chemistry to tell you about potential habitats and where to focus your effort and money. We're also concerned about water chemistry because bad water quality poses health risks to humans. If you've ever been around a Midwest lake in the summer, you may be familiar with cyanobacteria blooms. Some species of cyanobacteria can produce toxins that are harmful to humans, and many pets have died from drinking toxic water. Limnologists know that nutrients in warm temperatures fuel harmful algal blooms, and so understanding water chemistry is important for understanding water quality. And, on that note, I like to always ask people the question, is water quality better now than it was in the past? 100% of the time they say it was better in the past. And that's true if we think back far enough. Water quality was undoubtedly better before human development. However, we only have to look back about 70 years in the United States to see pictures of rivers that were on fire. So while we still have a long way to go to restoring the water quality of our nation's freshwaters, we've come a long way since the 1950s, thanks in part to the hard work of limnologists and legislation such as the Clean Water Act. So what is freshwater? Well, it's kind of a funny definition, because freshwater is relative to saltwater, and often we see definitions of freshwater in reference to their salinity, with freshwater being water that has a salinity less than 1 gram per liter, or sometimes 3 grams per liter. So what's in freshwater, other than water molecules? Well, if you were to take a cup of lake water and filter out all of the suspended solids, you'd be left with a mix of ions, nutrients, gases, metals, and organic chemicals. And the reason that there's so many substances dissolved in water is that because water is a polar molecule, it has an uneven charge distribution, with the oxygen atom being partially negative and the hydrogen atoms being partially positive. And so if an ionic compound is added to water, such as salt, sodium chloride, the ionic bond holding the sodium and chlorine together breaks, and the chloride, the negative anion, is attracted to the positive charges of the hydrogen atoms, and likewise with sodium and oxygen. And so in general, most salts, sugars, acids, and bases are what we call hydrophilic, or water-loving compounds. And these are compounds that will dissociate or dissolve into separate ions when added to water. Conversely, water is not a good solvent for non-polar chemicals, and these are substances like oils and fats. And we call these hydrophobic, or water-fearing compounds. These will not dissolve in water, which is why oils float on the surface of lakes. So what classes of chemicals do we find dissolved in water? Well, first off are our major ions, and we subdivide these into cations, or ions with positive charges, such as calcium, magnesium, sodium, and potassium, and anions, or ions with negative charges, such as bicarbonate, carbonate, sulfate, and chloride. We also have nutrients, and these are substances used by organisms to survive and grow. And the two most important macronutrients in lakes are phosphorus and nitrogen, and these come in many different forms, such as organic nitrogen, nitrate, ammonium, nitrite, phosphate, and many more. We can also consider silica a macronutrient, because some organisms use silica to build their skeleton, including diatoms, which are plankton that are ubiquitous in most lakes. Micronutrients, such as iron and manganese, are also necessary for growth, but are needed at much smaller quantities than macronutrients, such as phosphorus, nitrogen, and silica. Dissolved in water, you will also find gases, which is mostly oxygen and carbon dioxide, but also trace gases such as nitrous oxide and methane. And these can be important because lakes can be sources of greenhouse gases to the atmosphere. You'll also find dissolved organic molecules, which can be both natural and synthetic. The most well-studied and well-known organic molecule is dissolved organic carbon, or DOC. And this is because DOC plays a central role in lake carbon cycling and can affect water clarity. As analytical capabilities improve, limnologists are also starting to study human-derived synthetic molecules, such as pharmaceuticals and personal care products, as well as industrial chemicals like PFAS. And while we're not going to cover pharmaceuticals and personal care products here, it's good to remember that a lot of things that humans excrete can't be removed in wastewater treatment facilities and end up in freshwater environments. And just like caffeine, estrogen, or cocaine affects humans, it also can affect aquatic organisms. And we're finding more and more often that if you analyze water for pharmaceuticals, you'll find a wide range, from illicit drugs like amphetamines and cocaine, to stimulants like caffeine, pain relievers like acetaminophen, and also anti-inflammatories, antimicrobials, antidepressants, and other products like herbicides. But here we're going to focus mostly on the major ions that we find in freshwater environments, and we're going to focus on nutrients and dissolved gases in later videos. So when we talk about major ions, we focus on the 4 cations: calcium, magnesium, sodium, and potassium, and the anions bicarbonate and carbonate, sulfate, and chloride. And these are listed here in their general order of dominance, although as we will see, this is not always true. And just in case you're wondering, how am I ever going to remember cation versus anion? Well, here's one way. So how do we measure major ions? Well, these days we typically do it with sophisticated analytical equipment in a laboratory. And we do it by comparing water samples to reference samples that we know the concentration of. But to do so, we need a scale of measurement. And we typically report the measurement of major ions based on their concentration in water. And concentration is a unit of mass per volume. And we always use metric units in science. And so, for instance, we might have 5 milligrams of calcium in a liter of water. And so we represent this by saying 5 milligrams of calcium per liter, or 5 ppm, parts per million. We can also convert this to molar units, where calcium has a molar mass of 40.078 grams per mole. And so the conversion of 5 milligrams per liter is equivalent to 0.12 millimoles per liter. We will also refer to water as either having high concentrations or low concentrations of certain ions. But this nomenclature is relative, and is built up over years of measurements of water samples from a variety of freshwater systems. So sticking with our example of calcium, we know that if a lake has a calcium concentration of 10,000 milligrams per liter, that's a high concentration of calcium, as opposed to a concentration of 1 milligrams per liter, which is a low concentration. And looking at the periodic table, there's many different ions and different molecules in the mix. And so it's a lot of work to measure each ion individually and then add them up. So to make our lives easier, it'd be handy to measure the total amount of solutes in a water sample without worrying about which specific kinds or amounts. And we can do this by measuring the conductance or conductivity of a water sample. And this measures the ease at which an electric current passes between 2 electrodes. Basically, the more ions there are in the water, the easier it is to pass a current through, and therefore it's more conductive. So waters with high conductivity have a lot of ions, and waters with low conductivity have very few ions. The ocean has such a high concentration of ions that you're actually less likely to get electrocuted in the ocean, because the electricity would rather pass through the salty water than through your body. And we typically measure conductivity with a conductivity meter, which is much simpler than a measurement of individual ions. And conductivity is measured in the SI unit Siemens per meter. But inland waters are often very dilute, and so we tend to report conductivity in microsiemens per centimeter. For instance, Lake Mendota has a conductivity around 500 microsiemens per centimeter, whereas lakes in northern Wisconsin tend to have conductivities less than 100 microsiemens per centimeter. The conductivity of water increases with increasing temperature, and so often conductivity is reported as specific conductivity, which has been adjusted to some reference temperature, typically 20 or 25 degrees Celsius. And conductivity is related to other measurements such as salinity or total dissolved solids. Increasing conductivity means increasing salinity and increasing TDS. So we now know there's lots of ions in water, but where are all these ions coming from? Well, ultimately they're all coming from the weathering of rocks. Weathering is a process that causes rocks to break down into smaller and smaller particles, and eventually into ions. There are many different rocks on Earth, and they all have different chemical compositions. And those chemical compositions will determine what ions are weathered from those rocks. Also, different types of rocks have different weathering rates. So in areas of high weathering, local waters might have higher concentrations of ions than in areas of rocks with low weathering rates. So let's take a look at Wisconsin, which has a really unique geology. In the northern part of the state, the bedrock geology tends to be made up of igneous and metamorphic rocks, whereas in the southern half of the state, the bedrock geology tends to be sedimentary rocks. And those different rocks will weather different ions. So in the south, the rocks might be composed of something like dolomite, which is a sedimentary rock consisting of the mineral dolomite, which is a calcium-magnesium carbonate. And therefore, the major ions that might weather from dolomite are calcium and magnesium and carbonate. Conversely, in the north, we might find quartzite, which is a rock composed of quartz, which is silica oxide. Weathering of quartzite is very slow, but will eventually yield silica atoms. However, you can see it's not going to weather the familiar cations, like calcium or magnesium. And so generally, igneous and metamorphic rocks are very hard and very slow at weathering, and so they result in very dilute water. Whereas sedimentary rocks are softer and have faster weathering rates, and they produce ion-rich water, including silica, calcium, magnesium, and carbonate. And if you live in Madison, you might be familiar with these ions, because our drinking water is very rich in calcium, and so many homes have water softeners installed to remove the calcium from the drinking water so it doesn't scale up in pipes. And as we showed earlier, the ionic composition of inland waters tends to be dominated by calcium, magnesium, and bicarbonate, and this is because these are the ions that are weathered the most easily from superficial bedrock. Another source of ions to lakes, well, at least ones that are near the coast, are ions from the ocean. When wind blows across the surface of the ocean, breaking waves can lead to bubbles, which burst and inject seawater droplets into the atmospheric surface layer. Once airborne, these particles are deposited on land, usually through dry deposition. And you can see from this global map from the National Atmospheric Deposition Program that most of the sodium deposition in the United States is very close to the coast, and sodium deposition inland, in the Midwest, is less than 50 micrograms per liter, which contributes very little to the overall water chemistry of inland lakes. Other sources of major ions stem from human activities, and these include road salting, fertilizer application, and effluents that are discharged to surface water. And it's interesting to make the connection that just like ions in the ocean, ions that come from human activities are ultimately derived from rocks. So we still have geology to thank for major ions in lakes. And humans can have significant impacts on ion concentrations in inland waters. Here are the chloride concentrations from the lakes in Madison, Lake Mendota, Lake Monona, and Lake Wingra. And you can see in the 1940s that the chloride concentrations in these lakes were around 2 milligrams per liter. But 80 years later, these concentrations are above 50 milligrams per liter, and over 100 milligrams per liter in Lake Wingra some years. And in this case, the steady rise of chloride is the result of road salt application. And this is not unique to Madison. This is a common trend across the Northeast and Midwest states, where we see increasing trends in chloride in almost all urban lakes. And humans have impacted not only ions that are flushed in from the terrestrial environment, but have also impacted the atmospheric deposition of ions. A famous example is the emission of sulfur dioxides and nitric oxides from industrial smokestacks. And once in the atmosphere, sulfur dioxide is oxidized and then converted to sulfuric acid in the presence of water. And nitrogen dioxide is also oxidized to form nitric acid. Acids are then removed from the atmosphere by either wet or dry deposition. After limnologists sounded the alarm to the effects of acid rain in the 1970s, there's been a lot of legislation curtailing the emissions of sulfur dioxides and nitric oxides into the atmosphere. And you can see in these NADP maps, comparing sulfate and nitrate ion deposition in 1984 and 1986 to deposition in 2012 to 2014, that the atmospheric deposition of these ions has drastically decreased. So we've noted the sources of ions to inland waters, both from human sources and natural sources, including rock weathering and atmospheric inputs. But we should also talk about how in-lake processes affect ion concentrations. And these include evaporation, dilution, and sedimentation. Dilution works by adding water, and so therefore diluting the concentrations of ions. So if you had, say, 50 milligrams per liter of calcium and doubled the amount of water, you'd only have 25 milligrams per liter of calcium. And in a real lake, dilution will occur because of rain and snow that have ion concentrations typically below that of the lake water. However, a large rainstorm or a large snowmelt don't necessarily mean that the concentrations of ions in a lake are going to become diluted. Often rainstorms and snowmelt can bring in a lot of ions from the terrestrial environment and raise the concentration of ions in a lake. In contrast to dilution is concentration, which removes water from a lake and therefore concentrates ions. And this occurs through evaporation, because evaporation is the phase shift from pure water to pure gas and does not involve any of the dissolved substances we find in water. So in areas of high evaporation, like the desert southwest in the United States, we tend to find higher natural ion concentrations in lakes. Ions can also be removed from lakes through sedimentation. If the ion concentration gets too high, the lake may become supersaturated in ions, and the ions will precipitate out of solution. One unique phenomenon in lakes are whiting events, where calcium carbonate will precipitate out of the lake water. You can see this whiting event happening in a karst lake over 15 days in Spain, and you can see that the event gets its name from the chalky white color of the lake. And these whiting events can actually be associated with photosynthetic activity of algae, which take in carbon dioxide and raise the pH of the water, and this changes the carbonate solubility of the water, leading to calcium carbonate precipitation. Another example is biological sedimentation. For instance, diatoms use a lot of silica in their shells, and so when diatoms die and sink to the bottom of the lake, that silica will be buried in the lake sediments. We've referenced pH in this video, but now's a good time to look at pH and find out exactly what the scale means. pH measures the strength of hydrogen in water, and whether the water is acidic or basic. You're probably familiar with these terms, and know of common household substances that are acidic, like lemon juice and vinegar, and other household items that are basic, like lye and bleach. The pH scale ranges from 0 to 14, with a pH of 7 being neutral. 7 is the neutral point because that is the pH of pure water. pH is a logarithmic scale, with one pH unit being a 10 times change in concentration, and pH is measured as the negative logarithm of the concentration of hydrogen atoms in water. So we've already said that pure water has a pH of 7, which means it has a hydrogen ion concentration of 10 to the negative 7 moles per liter. But if a water sample has a pH of 2, that means it has a hydrogen ion concentration of 10 to the negative 2. That's 100,000 times higher than the water with a pH of 7. So why is pH important? Well, if the pH of water is too high or too low, aquatic organisms will die. For instance, if water becomes too acidic, the mucus on fish gills generally thickens, and this restricts the volume of oxygen that fish need to breathe. Another outcome is that at low pH, the calcium concentration in water is very low, and there might not be enough calcium for fish to produce eggs. At high pH, water will actually strip the fish of its slime coat and causes chapped skin on the fish. At high pHs, it's also hard for fish to dispose of metabolic wastes. pH also affects the solubility and toxicity of chemicals and heavy metals in the water, and so even if changes in pH don't directly kill organisms, the changing toxicity of their environment will. So most lakes have a pH between 5.5 and 9. And while pure water has a pH of 7, rainwater actually has a pH of about 5.6, and that's because distilled water reacts with carbon dioxide, forming carbonic acid, which lowers the pH. But rain with a pH less than this is said to be acid rain. But lakes tend to have a higher pH than rain, because of ions that are derived from the weathering of rocks that raise the pH. But there are naturally low pH lakes. Lakes with pH less than 2 exist, and these are usually due to volcanically produced sulfuric acid or human discharges of mine waste. Also, many bogs have low pH. Some sphagnum bogs have a pH between 3.3 and 4.5, and this is due to the exchange of cations for hydrogen ions by the plants. We can also have low pH lakes due to the atmospheric deposition of acid rain. Likewise, high pH is present in lakes as well. This is often due to high concentrations of carbonates found in saline lakes, and also can be a result of high rates of photosynthesis, which decrease carbon dioxide and increase pH. As previously mentioned, acid rain can be a major problem for lowering the pH of aquatic ecosystems, but the acidic discharge of mining wastes is also a major source of acidification in inland waters, albeit more localized than the problem of acid rain was. Because acid rain was so ubiquitous across parts of North America and Europe, the acidification of lakes caused a major problem, and to combat this, many lake managers took to liming their lakes to raise the pH of the water. Here you can see a picture from Sweden of a helicopter dumping calcium carbonate onto a frozen lake. Landmark research by limnologists on both the causes and the threats of acidification to lake ecosystems has strongly influenced emission control restrictions in the United States and Canada, and many lakes once threatened by acidification have since rebounded to natural pH. You can see our progress by comparing these two maps from the National Atmospheric Deposition Program of hydrogen ion concentrations in wet deposition between 1985 and 2018. Alkaline lakes with a pH greater than 9 also exist, and we call these soda lakes because of their high carbonate concentration. And this is usually sodium carbonate, and the lakes are usually saline or hypersaline. Interesting, these lakes tend to have very little to no magnesium or calcium, because if they did, the magnesium and calcium would bind with the carbonate and precipitate out carbonate as minerals, thereby lowering the carbonate concentration. Because of the high alkalinity, these lakes tend to have unique organisms that have adapted to life in a high pH environment. But even though we can classify lakes as acidic or alkaline, the pH of lake water is constantly changing due to physics, chemistry, and biology. Here's a heat map of the pH of Trout Lake over the last 20 years. You can see that within a given year, the pH ranges from 6 in the hypolimnion to over 8 in the epilimnion. What do you think might be causing this? Well, we see the differentiation of pH in the epilimnion and the hypolimnion because of stratification. But the actual changes in pH are happening because of biology. And we're going to learn all about it in our next video on oxygen and carbon dioxide.